Okay, good morning, everybody. Today we're gonna talk about the bioreactor engineering course. So this is the lecture 2 for this one. Today we're gonna talk about the mass balance, material, and energy balance. So I just focus on the chapter number 2, material balance, which is you need to balance the mass in and mass out to the process of your bioreactor or your fermenter. So the bioreactor or the fermenter is sometimes is they use in the same meaning. And the chapter 3 is about mass balance. For these two chapters is related to steady state, mean that all variable is not depend on the time. So, but in this chapter 4 is unsteady state, mean your material or your mass of your reactant or your product is depend on time. So this is overview of the of this section. And for the chapter about the material balance, so this is the step that I'm gonna talk about it today. So the first one is the conservation of mass, which means that your mass cannot be lost for somehow. So it might go to somewhere, but it needs to be conserved. Mean you cannot lose your mass, so you need to be careful about when you do the material balance. This is a step for calculation of this one, and then we have some example, and we can talk about some term in this particular is recycle. What is it? Bypass, purge, stream. So. And the last one is we need to talk about how we grow the cell. What is the stoichiometry to use in this process? Okay, before we start, we need to identify some term in thermodynamics. So imagine this is your system, and at the edge of your system, you need to identify what is your boundary of your system, and outside your boundary is your system. And let me ask you about what are these terms. What is batch process? What is semi-batch process? And what is the feedback process? And the last one, the fourth one, is continuous process. What is it? I let you think about it. So is sometime when you do some cell culture or you do some fermentation, you might need to use this one. In the industrial process, everything needs to be continuous. So you start you do your work all the time continuously. This is your answer. The batch process mean all reaction fit to the reactor or bioreactor in this sense at the beginning, and the product are removed or withdrawn when your reaction is complete. In the meantime, you are not going to feed your reactants, or you cannot withdraw the products during the process. This is the batch process. Everything needs to begin at the beginning, and everything is when it's finished. So you just remove it. This is the first one, batch process. And the other thing that more easily to understand is batch is everything is at the beginning and then you stop, right? And the second one is continuous process. So everything can be input it can be your action can be input all the time and output mean your products. So everything can be go in and go out at the same time. This is the meaning of the continuous process. You can see the difference. So I begin with the first one batch and continuous process. And if you don't have any kind of sense, so it can be this one. Semi-batch mean so it's in between these two, batch and continuous. Semi-batch, so sometimes you add or you remove your product in between. So semi-batch is in between these two. So but what is different between fed batch and semi-batch? Fed batch mean you only input your reactant but not remove your products. So this is only related to the reactant, your input. But if you cannot identify anything, so if you withdraw your product, so it can be semi-batch. That's it. My recommendation is you either identify what it is batch process or continuous process. And if you cannot categorize it into these two, so it's semi-batch. But if you feed your product, if you feed your reactant, it fed batch process. But otherwise it's semi-batch anyway. Okay, I think it's enough for this definition. So you can have a look later and you might come to this page again. Okay, the first thing that I want to talk about is conservation of mass. So you need to have these 5 terms in general. So accumulation means something that build up in your system equal to flow into your system. Flow into your system is which one? This one. Mass in your system minus mass out, and plus something that if reaction occur, it was generated. But if it is reaction, so you consume it. So you need to have this 5 term for general of conservation of mass. This is example of how to use this equation. So it's a continuous process. It's set up for treat wastewater. Okay, each day, this one, 100 kilogram, 10 to the 5 cellulose and 1,000 bacteria enter, okay, this one, into the feed stream. And cellulose, 10,000 kilogram of cellulose and 150 kilogram of bacteria leave. So this is mean this term out. This is out. The rate of cellulose digest it means you consume it, this one. By bacteria is this one. The rate of bacteria growth mean this one, you generate. And the death is this one. Okay. You need to use this equation to balance the mass of cellulose and bacteria. Okay. You can notice that cellulose is not generated in this system, but bacteria is either is grow or death in this one. The solution is in the other page, so we can have a look now. But the most important thing is this equation. You need to have a look at one more than once. Okay, this is cellulose. Cellulose is not generated, so it's only the generation is equal to 0. Accumulation is 20 kilogram of cellulose accumulate in the system each day. So what I said already is not generated, but it's different from the bacteria side. It's enter 100 kilogram. This one, bacteria, 1,000 kilogram. 1,000 kilogram of bacteria enter and live at this rate. Generate in this rate. All term is kilogram per day. So this one, total accumulation, the positive side means you accumulate this substance in your system. This one is cellulose accumulation, positive. Also, the bacteria is positive. So the bacteria is accumulate in the system, mean it's built up in your system. 5,000 kilogram of bacteria in each day. So again, you need to have this kind of concept first for the law of conservation of mass for this material balance. Okay, I think it's okay. Now we have a look in this one. This is how we do the material balance. This is all the procedure. Is the good idea that you need to have this step first. So the first thing is you need to understand your problems, your process first. So you need to have a very clear process flow diagram, show all the information. It's not the text, it's some diagram. All things you need to select your unit and your reactant. Okay, sometimes we need to have basis of calculation, like we feed this kind of reactant. All assumptions are applied to the problems. Like you use the ideal gas PV equal to nRT for your gas product, for example. And one more thing is your mass cannot be lost. Okay, and then you need to solve your equation. Okay, this is your step. Okay, this is the more important equation, and this is your step. And then we have a look first. This for this example. This one is the text. What I said before. You need to understand your problem. Is the corn steep liquor is alcohol that produced from corn, contain 2.5 invert sugar. Okay, it's about 2.5% of invert sugar, and the rest is water. Okay, no, not the rest. You can see it's not equal 100%. You need to have something like total is 100%. So this is some 52.5. So it's 47.5 is solid. Okay, you can notice from this text. This is the text. So you need to transfer this text into the diagram. And the bead molar contain 50% sucrose and inverted sugar. Okay. Again, your remaining is solid. It's mixed with corn liquor in mixing tank. So you need to have idea on this. Water is added also in another stream. Okay, and then this is your products. Again, 125 kilogram of corn steep liquor and 45 kilogram of molar. Molar is some sugar. Feed into the tank. You need to answer your question, this one. How much water is required for this system? Okay. Mass cannot be lost. Again, what is concentration of sucrose in the final mixing? This is your step. First, draw a clear picture first. assemble, analyze, calculate, finalize. So this is the step that we use. Okay, from the text, we have a corn stiff liquor. This part, okay, corn stiff liquor, and then this is the first stream. 255 invert sugar, 50% water, and the rest is solid. The other one is mollage. Mollage is 45 kilogram. This one, inverted sugar 1%, water is 18%, solid is 31 solid, and 50 sucrose. Sucrose is disaccharide sugar. This one, see, mollage, beet mollage, 50% sucrose, 1% sugar, 18%, and the remaining. So you need to identify the solid is 100 minus 50 minus 1 and minus 18. That is 31. Okay, and the other stream is water. Add to the mixing tank. So identify your boundary system, and this is your product. This is your product. So it's only 3 input and 1 output. Your product need to have 2% by weight of invert sugar. Okay, and you have p kilogram of your product, and you can identify more. So it needs to contain water, so solid, and sometimes sucrose. So everything needs to be identified here. All right, but the first question is how much water is required. How much water is required? So in this water stream, you only have water inside, no other things. Okay, once you assemble your flow sheet, so then you need to calculate the other one. Let's see first. Okay, this is all assumption. So your system has no leak, so no inversion of sucrose to reducing sugar or other reaction. Okay, this is more important because you need to state all your assumption first. Sometimes your reaction occur in different way that you assume. So you need to more be careful on this. So we don't think we need more extra data to calculate. So we have 125 kilogram of corn liquor, and compound are involved in reaction. Okay, we don't have reaction, right? I think we don't have reaction. Okay, it's a mixing tank only. Oh, we don't have reaction. No reaction occur. So we have only mass in and mass out. No accumulation also. This one 0. So we have only mass in equal to mass out. That's it for this system. Okay, this is your second step. Analyze, assemble, analyze, calculate. Corn stiff liquor. This is your inlet, and this is your outlet. This is your product. 2% product is P is mass flow rate of the outlet. Okay, this is your inlet. We have inverted sugar, we have sucrose, we have solid, and there is water. This is total. This is total. Okay, you have a look this table again. This is your inlet. So it's from this diagram, this flow sheet. And this is outlet. This is what you need to identify at the final. So let's see the final one. Okay, the mass balance is mean total inlet you have this equation 170 plus W equal to P. So this is more clear. This is 170 plus W equal to P. Okay, this is the first equation. And if we use invert sugar balance, mean this one, this is your product. Again, 3.575, this one, from this one to no, is 0.025 times 125 plus 0.01 times 75 equal to 0.02 P. Okay, that is this equation. Okay, you need to have a look. So, and we have this one, P equal to something. Okay, maybe the equation is not correct. Okay, for this one we have we have this is equal sign. So from this equation we have P equal to 178.75. Okay, and from this equation we can identify W is equal to this is not minus sign, is equal, this one is equal. Okay, is equal sign, is equal sign. Okay, let's see first. This one is equal sign. Okay, let me have a look on this one first. But is it fast enough? Let me see. Okay, this is not a minus sign, is equal. So we have W is equal 8.75 kilogram from this one. I think that is the first answer already. So we have W is water, so we have only this one, right? Okay. I think we already answered this question. Is 8.75 kilogram water is required, and the other one is concentration of sucrose in the final mix. Sucrose in the final mix, this one. So you need to have sucrose balance. So sucrose is from this one and this outlet. We have P already, 178 point something. This one, P equal to 1. Let me see why it's not working. Is it internet loss? Is it? Let me see first. Okay, I think it should be okay. So I just need to check the internet first. Should be fine, I think. I don't know what happened, but it doesn't sing anyway. Okay, let us continue. Okay, we answered this one, water. sucrose in equal to sucrose out, so we have this one, and the solid in equal to solid out, water in equal to water out. Okay, this is how we have a look on this one. Okay, you can have a look on what I already give you to this one. So it's our course on Moodle. Okay, this is the one. Okay, let me see first. 4.4, right? Example. Okay, this is 4.3. Okay. Okay, this one. Okay, is P equal to this one. This is water, is liquid. Okay. And this is water out. Water out is this one. Finalize is okay. The product is contain 13% of glucose. Is around 13% of glucose. So this is sucrose outlet, and then this is the outlet of all the stream. Is around 13% of sucrose. The first one is 8.75 kilogram of water is required, and the mixture contain 13% of sucrose. Okay. I don't know why this doesn't work. Let me see first. Okay, I cannot write down anything. Okay, should be fine. I should be okay. Let us continue first. Okay. Okay, this one. So we have this, and this is all the answer that I mentioned before. This one. Okay, you need to summarize this one into the I think you have a clear picture from the problems and identify the process, and then you calculate something and put into the table. And for this one, you have something to recycle back. This is recycled stream, because sometimes we just want to have more reaction, so we have more conversion. Conversion means your reaction convert to other to the products. This is bypass, so you not enter the process, you just bypass it. And then your purge means sometimes we have gas CO2 as product, so we just purge it out, because if the gas build up in your system, so sometimes it can generate more pressure, so it's more dangerous to your system. So we have recycle, bypass, purge for clarify this process. What else? This is fermenter with recycled cell. So some cell is recycled back to your fermenter or your bioreactor, for example. And sometimes this is reactor tank, bioreactor, and then this one is separator. I mean, reaction is not occur here, but you separate something, you separate products to the packaging line or something like that, and you are recycle some cell back to the process. This is the meaning of these two. What else? Oh, okay. You can have a look on this one, but I cannot write it down. I don't know why. Wait, let me see first. Okay, this Can I write it down? Okay, you have what is overall conversion? What is single pass conversion? The overall conversion, you just highlight everything. You have reactor here, bioreactor, for example. You have separator here, and this is how we calculate overall conversion. You can have a look first. Single pass is you just consider only this part. Okay, this is single pass. Let me have a look on this one first. Okay. Maybe I can write it down. Yeah. Wait. Can I? It doesn't sing anyway. Okay, let's try another way. Page. Okay, note. Continue. Let me try using the notes first. Bioreactor. Engineering. Okay, let me see first. Dun, 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 dun. Wow, wow. Still sinking. Okay, we have it here. It's sync. Bioengineering, bioreactor engineering. So, okay, what is the single pass and what is the, let me see first. Okay. Okay. Single pass is just you draw this picture. Your reaction is from A to B. Reaction is from A to B. So single pass is this one. 75 mole of A convert into 75 mole of B. So you have 100% overall conversion. That's it. So you have overall conversion is everything here, around here, and then you have 75 to 75. But the single pass, this one, you only have 75 mole of B from your reactor, but you have 100 mole of A. So this single pass is only 75%. The single pass is only 75%. Single pass conversion. So this is what I try to mention here. The single pass is only 75%, but the overall conversion is 100% conversion. Okay. This is what this slide try to mention. What else? Okay, you have your answer from this one. This 100. This is 75. What else? This one. You can have a look on this. So you write down the mass balance. So in this case, you need to have a look on this one first. You have a look on this one first. So it's also in Thai, but I will translate to you. So is you have two mixture, 50% of toluene and 50% of benzene. The enter is 10,000 kilogram per ounce. You have this one outlet, these two outlet. First, you just draw the picture from here first. It's called overall mass balance. It's called overall mass balance. Is overall mass balance. This one. Overall mass balance is this one. So you only have these two. Let me see first. So you have 10,000 kilogram per hour in, right? And then you have this one, 6,000 kilogram per hour at the top here. And simple calculation, you have 4,000 kilogram per hour at the bottom. Okay, this one. You have 6,000 kilogram here, and then you have 4,000 kilogram here. Okay, this is overall mass balance. Okay, and then what this I try to ask you is, what is the mass fraction of toluene at here? So you just use toluene balance. Toluene balance. Okay. So you have 0.5 times 10,000 from the inlet equal to x times 6,000 at the top. At the top here is toluene fraction plus 0.96, so times 4,000. So you just have toluene balance here, which is this one. Your next step is identify X is mass balance of this one. I guess that you can do that, right? You might pause the video and then you can do it. And then you have this kind of answer. The answer is still in here. So you can have the idea what is the value of X that I mentioned here. Okay, do some more calculation, please. What else? This is more example of the mass balance. So it's a bacteria. So some organism. When you talk about the organism, you need to have this kind of how to write down their names. So it's Acetobacter aceti. So it's italic alphabet. So for the name of the microorganism. So this bacteria convert ethanol. Ethanol is C2H5OH to acetic acid under aerobic condition. Aerobic means you have to have air in your system. A continuous fermentation process for vinegar production. So vinegar is some alcohol, but you have this sour taste. Is proposed under non-growing. So this is short term of this bacteria. Immobilize. You stick your cell into some surface. So this one they use gelatin bead to immobilize the cell, so it cannot be moved to other things. Air is pumped into the fermenter at the rate of 2000 gram mole per ounce. The production target is this one, acetic acid, and the maximum concentration tolerance by the cell. So you cannot produce a lot of acetic acid because it's toxic to the cell. Okay, this is your question. What is minimum amount of ethanol is required? What is minimum water must be used to dilute ethanol to avoid some toxic to our system? And what is composition of off gas? So it produce some gas. Okay, the answer is in your book. Okay, I just explain the problem first. Okay, and then we have more example on 7.4 Isotope Distillation. What is it? Okay, and we come to the last section of this lecture. So it's stoichiometry of cell product. So you need to have substrate. Substrate you contain carbon, hydrogen, oxygen, and nitrogen. You need to have oxygen to for them to use in their breeding or their growth. You need to have nitrogen source, GH. So it's something that is chemical formula. You have the biomass here. You produce some CO2 and water. So this is how cell convert substrate for cell growth. So you have built up some biomass. So in the book they also have the biomass formula for you to use it. Okay, let me see first. This is how we grow, and I think okay, and then we go to the energy balance. So for this one, we single protein for hexadecane is described by reaction. So this is hexadecane, this one, and use oxygen, and we have ammonia as a nitrogen source, and this is the biomass that produced from this reaction, and you produce CO2 and water. Okay, this is how biomass. So it's also written in this book, and RQ is this one. You just balance it. Carbon, you have 16 here. You have C times 1 here, and you have D here. So this is carbon. Hydrogen, you have 34 here, plus this side B times 3, and where is this one? C times 1.66 here, and you have 2E. This is hydrogen. Oxygen, 2 times 1 equal to C times to 7 and do 2D here, and you have E. And nitrogen, RQ mean D divided by A. D is, this is mean RQ. D is mole of carbon dioxide produced, divided by A is oxygen that you use. Okay, is RQ. Is also in your book. Is carbon dioxide produced that divided by oxygen that you use, all in mole. So you have many equations. So your target is just to solve this kind of equation, and then you come up with the things. And this is biomass yield. Is a definition of cell produced divided by substrate consumed. Cell produced divided by substrate consumed. This is the mean of biomass yield. Okay, we don't have this answer for this one, but the final one you need to have this thing: A, B, C, D. This is, you have 1, 2, 3, 4, 5 variable, and you have 5 equation here. You need to do this one. Okay, I think it's not hard for you to do it. Okay, what else that we want to say? This is definition of the yield, and this is what I mentioned here: isotope distillation. Isotope is something that you cannot separate them more from distillation, or you like ethanol and water, so you cannot separate them from 95% to 5% of water. You need to have more process on how to separate it. I think this is the one, right? So this is the process. Is called Kai distillation. Kai, this is one. This is a mixture that you cannot separate it. 95% ethanol and 5% water, and you need to have this kind of what is called solvent. You put benzene here, and you do some distillation, and then you can have 100% ethanol at the bottom. And the other thing is you have this one, but you do more separation. This is what we try to mention about isotope distillation, because you cannot, with a simple distillation without this benzene, you cannot produce 100% of ethanol, for example. This is how we do it. Absolute or 100% ethanol is produced from mixture of this is isotope mixture, 95% ethanol and 5% water, and this process is called Keyes distillation process. A third component or solvent is added. In this case is benzene, to lower the volatility of alcohol. Under this condition, overhead product is produced: 18.5% ethanol, 7.4 water, and the benzene is the rest. When we do some mass balance, we are not using volume, we're using the mass balance. So this is how the process is. I think for today I might stop the video here and then let you enjoy how we do the mass balance for this one. So you need to have this kind of idea first: assemble, analyze, calculate, finalize. This is how we do the some step. Okay, I let you do some revision and then enjoy the mass balance. See you in the next lecture. Thank you for today. Bye.